Hello physics students. Today's topic is standing waves. And what I'm going to do today is I'm going to begin our video by demonstrating what standing waves are and how they're created. To demonstrate standing waves, what I have here is a spring that stretches across your view from the entire length of the screen. At that end, the spring is rooted to a table leg. So that end is not able to move, and that end, I'm going to be at that end shaking the spring. Now, the reason why I chose this spring is because waves on this spring moves faster than on the slinky, so it'll be work better for our demonstration. So if you watch, see how fast that moves, more conducive to creating our standing waves demonstrations. But I want to point out something that is important for standing waves, but in all waves, that the speed of a wave in a material does not depend on the wavelength, the frequency, or the amplitude. Like, for example, sound. The speed of sound is 331 at STP. Doesn't matter if the sound is quiet, if it's loud, if it's a bass guitar, or the treble of a cymbal crashing. All of them travel at the same speed. And you could see that here. If I send a small wavelength, you see how quickly it shoots across the screen. If I send a big wavelength, a big amplitude, small amplitude, big amplitude, it went the same speed. Also, if I try and send a short wavelength, it goes fast. If I send a longer wavelength, it also goes fast. Same speed, regardless of what kind of wave I'm sending. So what I'm going to do is show you what a standing wave is. So this is sometimes a little tricky. Let me try again. So as you could see, you see this spring vibrating up and down in your view. And you don't see any side-to-side motion. That's a standing wave. It's standing in one place, neither moving left nor right, only moving up and down. So, but I want to say that that is actually an illusion. There are waves moving side to side. It's just that there's one wave heading this way and another wave heading this way. And when they meet in the middle and interfere, it creates the illusion of one wave, not two, that's staying still horizontally, standing in place. And you might be saying, well, how could there be two waves if I was only at that end shaking and at that end was a table leg? Well, if I had someone here, I could have asked for a volunteer to shake at that end. But I don't have anyone here. I'm recording this video by myself. So what I utilized is the fact that when I send a wave at a fixed point, it reflects. Let me show you. You already saw it, but if I send a trough, it flips up as a crest. If I send a crest, it flips over as a trough. So the other source of the wave is me. I send waves this way, and then they reflect. And if I keep sending them this way, they keep reflecting this way. The table is my partner, producing an identical wave. I'm going to try and set up the fourth harmonic again, and then at home I'm going to try and make it go in slow motion. And you'll see a wave traveling this way in slow motion. And then, as soon as it starts reflecting at the other end, it starts bouncing back, and the wave that was going this way suddenly looks like it stops moving because it's actually two waves moving past each other. So let's see if I could hit the fourth harmonic for my little slow motion special effect. There it was, not bad. So hopefully what you saw I was using a word, by the way, that you don't know yet. I was jumping ahead, I forgot. But what you hopefully saw is the wave traveling this way for a brief moment, and then as soon as it reached that end and started reflecting, it looked like it stopped moving side to side, and it was standing frozen. So you could really see that that was an illusion, okay? Now, let me create that 4-segment wave again. Let's see if I could do it. So you see 4 segments. If you were to, you probably see it in your view better than in my view. And I can't get up to show you, but you see one segment here, another segment, and then the 3rd segment, and the 4th segment at that end vibrating back and forth. Those are called what we call antinodes. And don't worry about writing that down. I'm going to write that down on the board later. But the points that move with maximum displacement, maximum vibration, are called antinodes right here, there, and there. So I have 4 antinodes right now. Right here is the point that's hardly moving. Right? You see that? And then there's another point right in the middle. There's actually a little piece of tape on the floor. And then there's a 3rd point in the, that's not moving. And also the ends of the spring are not really moving much. Those points that don't really move much are called nodes. Nodes don't move. Antinodes move with maximum displacement. So if you were to count those, you would have 4 antinodes in that wave and 5 nodes. But I could create different number of antinodes if I shake my hand here at different rhythms. So what I'm going to do now is I'm going to set up what we call the first harmonic. If I shake slow, this is what we call the first harmonic. It's the simplest possible wave we can get vibrating on this spring. Notice in the middle there's one antinode, a point that's really moving rapidly, and then at the ends, nodes. Now my hand's moving a little bit to keep this driving because of the friction. But if there wasn't any friction, I could stop my hand and this wave would keep going for a while all by itself, and this would be truly a node. But the first harmonic, which this is, has one antinode in the middle and 2 nodes at the end. Okay, so, and notice that frequency. If I time this with a stopwatch, I could then do 1 over that period and get the frequency, and the frequency would be 1 vibration, 2 vibration, 3 vibration, 4 vibration, 5, 6. It's slower than 1 vibration per second. The frequency might be like, I'll make up a number, like maybe like 0.7 or something like that. 0.7 would be, I only get 0.7 vibrations in 1 second. So pretty slow frequency. Now I'm going to shake my hand over here faster. And what you see is now 2 segments instead of 1, right? We had 1 segment, that's the first harmonic. This one has 2 segments, and so it's the second harmonic. Notice there are 2 antinodes, one somewhere around here and one over there. And if I were to snap a picture of this, it would be like one sine curve with a crest and a trough, or trough and a crest. Also, there are 3 nodes, one here by my hand, one in the middle, and one at the end. So 2 antinodes, 3 nodes. Second harmonic, 2 antinodes. I'm going to shake even a little bit faster. And now you see what we call the third harmonic. So count the antinodes. There's one here, one right in the middle, and one at the far end over there, near the far end. That's 3 antinodes. Either a crest or a trough is an antinode. The nodes, there's one here by my hand. There's one somewhere right over there, one further there, and one at the end. There are 3 antinodes and 4 nodes in the third harmonic, 3 segments. Now what I'm going to do is shake even a little bit faster and make the 4th harmonic, which we already saw. Oops. You got to get the rhythm just right. There we are. There's the 4th harmonic, 4 antinodes, and 5 nodes if you were to count them. 4th harmonic, 4 antinodes. And maybe I'll try one more, the 5th harmonic. Is this the fifth? One, oops, 1, 2, 3, 4, 5. There it is. That's the fifth harmonic. If you count the antinodes, you've got 5 of them. Oops, I'm messing up. There it is. 5 antinodes and 6 nodes. So there it is. But notice how fast that is, because the wavelength of the fifth harmonic was short. It was like this for a crest and a trough was short. Whereas the third harmonic, or even the second harmonic, the wavelength here is long. It's the whole spring. So with a bigger wavelength, long wavelength, big lambda, small f. If I make a shorter lambda, like here, lambda's only to there, shorter lambda, bigger frequency. Because again, V equals lambda times frequency. The V is the same. No matter how fast I shake here, it has the same speed. So if I make one bigger, the other gets smaller and vice versa. So those are standing waves. Let's go to the board and summarize everything that we learned in these demonstrations. So let's summarize everything that I talked about on the floor. Now, before I begin, I just want to warn you, don't copy this yet because I'm going to put the first harmonic here. So if you copy this and then that, you're going to be out of order in your notes. Because the first thing that I want to get into your notes is how standing waves are created. So again, as I mentioned earlier, that one way to create standing waves is to have 2 people at opposite ends of a spring or a rope or something like that, and both people shake and make the same waves. In other words, the same amplitude and the same wavelength. As these come here, they're going to constructively and destructively interfere at different times, and they're going to be 2 waves traveling in opposite directions, but it'll look like there's no side-to-side motion. It'll look like there's just up and down vibration. The other technique, as I mentioned, was if I didn't have another person, I just can send my waves at a wall or any fixed point, and the reflected waves will serve as the waves coming from person B over here. So one person sends a wave, continuous waves at a wall. So go ahead and copy these down. All right, now, so as I said, I'm going to erase here. The next thing we're going to put here is the first harmonic. So hold off on this. All right, so here I've drawn the first harmonic, and so this would be what you would see if you were hovering above me, shaking the spring, and you snap the picture when the spring reaches maximum displacement. So as I already briefly mentioned, the points on a standing wave that never move are labeled nodes. So N is a node, and AN is what we call an antinode. So antinodes are points that have the maximum displacement along the spring. In other words, the exact crest or the exact trough of a wave. Of course, a split second later, the spring will be down here, so it'll be oscillating like this. Antinode, whether it's up here or down here, always an antinode. These are nodes. So if you look at the first harmonic, then basically we can see that the first harmonic has 1 antinode and 2 nodes. Now, what is the wavelength of this particular wave? Well, if you look at this picture over here, you would see that this is actually not a complete wave. A complete wave doesn't just have a crest. It has a crest and a trough, or a trough followed by a crest. But both crest and trough are a full wave. So if I were to make the rest of this wave, what I would have to do is add a trough. So I would go like this, and there. Now that's one complete wavelength, crest and trough. So the wavelength is here. Now notice that is, if this is the length of the spring, I don't know, 3 meters or whatever it is, then this is double that. So we could say as a math expression that the wavelength here is twice the length of the spring, whatever it is. Now, we can relate the frequency and the wavelength from the equation that we've been using with waves all along. V equals lambda times frequency. As I mentioned, this is the same in the spring no matter how you shake. It's only a function of the spring coils, how, how thick they are, how rigid they are, and how tight you pull it. So it doesn't matter how you shake like this. That's the same for all of these waves. So we have a certain wavelength here. The frequency at which we produce the first harmonic is actually called the fundamental frequency. So that's a term you'll see with standing waves, only for the first harmonic. All right, so if you need a moment to catch up, copy these notes, and in the pause that I'm going to create, copy these down. Second harmonic. So as you saw, I shake fundamental frequency, and then if I shake faster, I make the second harmonic if I match the rhythm and I get it just right. So here's a picture, if you were to snap a picture, a photograph of the second harmonic, and if you snapped the picture at a slightly later time, you would see, instead of a crest followed by a trough, you would see a trough followed by a crest. So either way, it's still the second harmonic. Either way, these points are still both antinodes. Either way, all three of these are nodes, they never move. So in the second harmonic, we have 2 antinodes and 3 nodes. 1, 2, 1, 2, 3 nodes. I forgot to mention here, this is the amplitude. Remember, the amplitude of a wave is not from crest to trough. It's from the equilibrium to crest or equilibrium to trough. So we could label this amplitude also here. Now, if you look at that wave, it is one complete full wave. We've got a crest and a trough, so that's one wavelength. In other words, the wavelength of the spring is just the length of the spring. I mean, the wavelength of this wave is just the length of the spring. So if the spring is 5 meters long, whatever it is, then that's what the wavelength is. So once again, we have this equation. As I said already 2 other times, this stays the same. It doesn't matter. Just think of sound, like regardless of what kind of sound you're making. V is 331 at STP. Regardless of the color of light, red, blue, green, all different frequencies, all different wavelengths. Speed of light is always 3 times 10 to the 8th. So speed of wave on a spring is always, 8 meters per second. Whatever it is, it's the same in all harmonics. So what we've done is, if you notice, the wavelength just got shorter. In fact, the wavelength got half as big as the original. What that means is the frequency in the second harmonic is twice the frequency of the fundamental frequency in the first harmonic. So second harmonic, double the frequency. All right, if you need a moment to catch up, I'll create a pause to allow you to copy these notes down. All right, next one, we're going to do third harmonic here. So give me a moment. Okay, so here is the wave pictured in the third harmonic. If you were to snap a picture from above, click like that at that moment, that's what the wave would look like. If you snap the picture slightly later time, you might see this instead. Again, whether this is a crest or trough doesn't matter. It's going to be considered the antinode, antinode, antinode. So in the third harmonic, we have 3 antinodes. And in the third harmonic, we have 1, 2, 3, 4 nodes. Oops, I guess I'll have to scrunch it in right here. So the pattern, if you look back at the first harmonic, which I erased, you would see that the first harmonic has 1 antinode. The second harmonic has 2 antinodes. The third harmonic has 3 antinodes. Do you see a pattern? Well, obviously, it's just the number of antinodes is the harmonic number. And there's always 1 extra node compared to how many antinodes there are. Now, this is a little bit more, an amplitude is right here. This is a bit more tricky to figure out the wavelength. So in class, I would ask you, anyone figure it out? And some people would. They'd be clever enough based on this length of the spring. If you don't see it, that's okay. Let me explain how it's done. So what I want to do first is the first thing you could note is there are 3 equal segments. This standing wave breaks the spring up into 1, 2, 3 equal segments. So what I could do is I could find the length of one of those segments right here. This is the length of the spring over 3. In other words, if this were like 6 meters, this would be 2. 6 meters, 2, 2, and 2 would be a total of 6 meters. This would be 1/3 of the whole length of the spring. But that's not a wavelength right here. A wavelength isn't just a crest. A wavelength is a crest and a trough. So whatever this distance is, we need 2 of those to get a wavelength. And that's the wavelength. Whatever the length of the spring is, divided by the length, by 3, the antinode number, and then multiplied by 2. And then you just punch that on a calculator. You get the wavelength just from geometric considerations. The next thing, again, once we know the wavelength, we can use our classic wave formula here. Again, this is the same. Doesn't matter what harmonic number it is. It just depends on what kind of spring you're dealing with. So now what happened is, if you remember, the original wave was twice the length of the spring. So what we have is 2L over 3. In other words, now the wavelength is shorter still by 1/3. Well, if this has got to be the same, and I just made this smaller, I have to make this bigger by the same factor in order for this equation to hold. Okay, so the frequency will be 3 times the amount. So the fundamental frequency was slow, the third harmonic 3 times as fast, and you'll set up the third harmonic. All right, so let me create a pause to give you a chance to copy these notes down if you need a moment to catch up. All right, so next thing, a pattern. So I guess I leave this here. Well, I could erase it. So in the first harmonic, we had a wavelength of 2L, twice the length of spring. Then we had a wavelength, I'm going to leave a little space here, of L for the second harmonic. And then in the third harmonic, what we had is, let's bring this 2 up front here. Okay. It's the same formula if I bring the 2 first, right, and bring it in the top. So can you write a formula in general for the wavelength of any standing wave? Again, I would ask for hands in class, but we're not in class, so maybe you see it. Maybe you want to, stop the video and think about it for a little bit. But it becomes easier if I do this. If I say 2 over 2. I didn't change that number. It's still multiplying it by 1. 2 over 2 is 1, so I'm multiplying 1 times L. But now you see, in all harmonics, I've got 2L on the top. And then, let's add this. I didn't change anything when I divide by 1. And what you could see is 1, 2, 3 in the bottom. In other words, the antinode number. That's the wavelength in any harmonic, okay? Now, that's not on the reference table. So this is one of those like the one in the electrostatics unit where the charge was equal to the number of electrons times EQ equals NE. I said not on the reference table, but part of the curriculum. Same thing here. This is still, you have to be able to do this even though this isn't on the reference table. So I think the way they have you do it is by reasoning out, like I did over here. So you just got to reason it out. So let me create a pause to give you a chance to copy that last equation down. All right, what I want to do before we finish for today is an example. So hold on, bear with me. Okay, here's the problem. We've got a 0.64 meter long guitar string vibrating in the fifth harmonic. Waves travel at 17.8 meters per second on the string. Sketch the wave, part A. B, label the nodes and antinodes. C, determine the wavelength. And D, determine the frequency. By the way, I'll talk about it more before we close out here today. But these standing waves are a big part of guitar playing or playing any string instrument, violin, cello, whatever. Basically what you're doing is you're creating these standing waves. If you could photograph these strings vibrating, if you know, with a high-speed camera, not just a regular camera, one could take very fast pictures, you would see this in different modes of vibration, different, you know, first harmonic, second harmonic, third harmonic. I'll talk about it a little bit later. So the first thing, sketch the wave in the fifth harmonic. So what I'm going to do is just start here, and then I'll just start drawing 5 antinodes. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. All right, easy enough, and I'll just end the wave right there. So now I'm going to label all the nodes and antinodes. Here's a node. And, oh, forgot one. -1 right here. So, antinodes are either crests or troughs. Doesn't matter. They're both antinodes. Okay, so there it is. That's A and B. Okay, so yeah, let me create a pause to give you a chance to catch up if you need it. All right, part C. So I erased the formula here. Again, you know, on the Regents, you don't get your notebook, so, and it's not in a reference table. So what if this came up on the Regents? What you could do is what I did before. You could say the wavelength is equal to the length of the string, which is 0.64 meters. And then what I'm going to do is find the length of one of these segments. So I've got 1, 2, 3, 4, 5 segments. So let me find just this length right here by dividing the length of the guitar string by 5, because that's how many segments I have. So right there is this length that I shaded in that diagram. But that's not a wavelength, it's only a crest. A wavelength is a crest and a trough. So I need to extend this length to include a trough, which means I'm just basically taking this and doubling it. And so I go like this. And so the wavelength, I think I got it out here. Okay, good thing. I calculated ahead of time, 0.256 meters. There's the wavelength. And then finally, part D, the frequency. So I use this V equals lambda times frequency. So this one, since it's not on the reference table, I didn't write out a formula because it's not even there for us to use. But this, you got to write the formula, as I've mentioned all throughout the year on the Regents. Any formula on the reference table, you got to start your calculation by writing it out. 17.8. The wavelength I just figured out, 0.256 meters. And the frequency is unknown. So what I'm going to do is divide both sides by this 0.256, and I get frequency of 69.5. Let me create a pause to give you a chance to copy these notes down. Okay, so that's it. Example, we did the notes example. Now I just want to summarize, and what you want to do is go back in your notes and make sure you know the 2 ways you could create a standing wave right at the beginning of the notes. Make sure that if you had to, you could sketch any harmonic, okay, 4th, 5th. All right, maybe they're not going to go to the 20th. That gets a little silly. But the 1st, 2nd, 3rd, 4th, 5th, any one of those could show up on the Regents. And then you also want to be able to label all the nodes and antinodes and show where the amplitude is, right? These are all things that you might have to do on the Regents. And also how you figure out the wavelength and then apply this formula here. And then also the general patterns that as you go up in harmonics, the wavelength gets shorter. So smaller lambda, bigger frequency. You have to shake faster to make the higher harmonics, as we saw on the floor. So that's the physics. Now, one last thing I want to mention. I mentioned briefly string instruments. So really fascinating stuff. Some of these guitarists. I saw an interview with Eddie Van Halen You may have heard of Eddie Van Halen. He recently passed away, unfortunately. A very famous guitar player in my time when I was young. People, concerts, 100,000 people, would go. But he was legendary. He was a master guitar player, which really meant, in his own way, he was a master physicist when it came to sound and how to create these different modes of vibration. I mean, you're going to puzzle through this on the homework. Eddie Van Halen, when he played a solo, you couldn't even believe it. He's hitting these harmonics in split seconds, different harmonics, so fast in his brain, just like a genius with these harmonics and knowing what frequencies it makes and how it makes music. Now, I'm going to search YouTube to find that video of that interview. As he's an older man, he's in his 50s, shortly before he passed away, I believe. But he plays a solo, and I was watching it like in awe. Like I mean, I don't even know if I could even understand fully what he was doing, even as a physics teacher. Just tapping the strings in all these crazy places, making this crazy music and sound out of a guitar. So real treat. But if I do find it and put it in the stream, it's optional. It's just only if you're interested in guitar players and seeing kind of what kind of mastery is possible with these standing waves. So that's it for today. I hope you enjoyed the demonstrations. I hope you enjoyed the physics and you understood everything. I'll see you in the next physics video.